So other indeterminate forms, and this might be infinity times infinity, infinity times 0, infinity minus infinity, 0 to the 0, infinity to 0, 1 to the infinity, infinity over infinity, or negative infinity over negative infinity. So for these actual ones here, like these first three, these you can use L'Hopital's rule for, all right? So as long as you verify that you have 0 over 0, or infinity over infinity, or negative infinity over negative infinity, then you can use L'Hopital's rule. So let's go ahead and try this today. So we have limit as x approaches infinity of natural log of x over x. So what do you know here? Well, natural log of x is as x is going to infinity. Remember that this actually looks like, all right, it looks like this. And so that means as x is going to infinity, the numerator is going to infinity. And then as the denominator is going to infinity, it's also going to infinity. So that means that we verified that L'Hopital's rule can be used. So L'Hopital's rule can be used here. So now let's apply it. So limit as x approaches infinity of the derivative of natural log of x, which is 1 over x, over the derivative of x, which is 1. So then the limit as x approaches infinity of 1 over x is actually 0. All right, so that is the first one right there. So hopefully that all makes sense of how L'Hopital's rule can be used in this particular case as well. All right, here's another one. Limit as x approaches negative infinity of x squared over e to the negative x. So what do you know here? Well, all right, so y equals x squared. That actually looks like this. So as x is going to infinity, the value is going to infinity, and then e to the negative x is 1 over e to the x. So what is that actually going to look like? Well, that one is, oh boy, well, here, it's, I'm telling you, all right, so it's actually, it looks like this, all right, so as the x is going to infinity, the y is actually going to infinity also. So this is actually, in, actually, oh, by the way, did this say the I'm trying to double check because I feel like I I said something that might seem a little bit strange to you here, so I want to make sure that I didn't actually upset the system here, because I think I wrote down the problem wrong. So I just want to double check that I didn't write down the problem wrong here. So if I did, then I apologize, but I'm going to double check here. So yeah, okay. My apologies. I, I did actually write down the problem wrong, because well, I did, but in not, well, I should just put a negative in front of this, but I did write down the problem wrong because I'm looking at this. All right, so yeah, so this one actually looks like, um, looks like this. All right, so now, since I thought that said infinity, not negative infinity, I actually need to look. I need to look as x is going to negative infinity. So as x is going to negative infinity, you see you have infinity over infinity. So this will be limit as x approaches negative infinity of the derivative of x squared, which is 2x, over the derivative of e to the negative x, which is negative e to the negative x. And then if you go ahead and you do this again, you realize that you will have a form that is negative infinity over negative infinity. And so that means I can apply L'Hopital's rule again. So that will give me limit as x approaches negative infinity of the derivative of 2x is 2, and derivative of negative e to the negative x is e to the negative x. And so then this actually ends up being, well, as e to the negative x, as x goes to negative infinity, that becomes really, really large. It's approximately 2 over some really large number, which gives you 0. So this limit ends up being 0. So the first one was 0, this one is 0, and now let's try for the next one. Again, if you have any questions about that, let me know. But here, let's try this one. We have the limit as x approaches a half of secant of 3 pi x over tangent of 3 pi x. So what do we know here? Well, all right, secant of 3 pi x is 3 pi over 2, and tangent of 3 pi x would be 3 pi over 2. So the numerator, that's 1 over the cosine of 3 pi over 2 over the, well, sine of 3 pi over 2 over the cosine of 3 pi over 2. So what do you have here? Well, in the numerator, 1 over 0. In the denominator, negative 1 over 0. So you don't have, this is not, it's not 0 over 0, infinity over infinity, or negative infinity over negative infinity. So you cannot use the L'Hopital's rule here. All right, so what are you going to do here? Well, you're going to do almost exactly what I just did, but not substitute in the x, all right? So it's going to be limit as x approaches 1/2 of 1 over the cosine of 3 pi x, and then I'm going to multiply by the reciprocal, so cosine of 3 pi x over sine of 3 pi x. So those divide out, so I have limit as x approaches a half of 1 over sine of 3 pi x, so that's, well, 1 over, all right, sine of the 3 pi over 2 we just said was negative 1, so 1 over negative 1, which means that this limit is equal to negative 1. So hopefully you enjoyed that, but that is the end of dealing with that type of format here. So let's try a little bit of a different one here. So here is one on the infinity times 0 or 0 times infinity, all right? So the limit as x approaches infinity of e to the negative x times the square root of x. So this is e to the well, if you think about it, it's e to the negative infinity times square root of infinity. If you think about it in that terms, then what you see here is actually that you have a 0 times an infinity form. So that's this form right here. But you can only use L'Hopital's rule for 0 over 0, infinity over infinity, and negative infinity over infinity. So that means that since this is not in the 0 over 0, infinity over infinity, or the negative infinity over negative infinity form, then that means that we need to rewrite the e to the negative x times square root of x. So how am I going to do that? Well, I can rewrite it as the limit as the x goes to infinity. So why don't I rewrite it as square root of x over e to the x. And if I do that, then I can see that this is in infinity over infinity form, which means I can use the L'Hopital's rule. So all I did was I moved that to the denominator with a positive exponent so I could use L'Hopital's rule. All right, that's all I really did. All right, now I use L'Hopital's rule. So that's the limit as x approaches infinity. The derivative of the numerator, if I make this x to the 1/2, is 1/2 x to the negative 1/2 all over e to the x. So then I will rewrite this limit as x approaches infinity of 1 over 2, and then I'll bring this to the denominator as square root of x and then e to the x, which you see is approximately 1 over some really large number, which happens to be just 0 then. So this limit is equal to 0. But again, I needed to rewrite it because it needed to be in 0 over 0, infinity over infinity, or negative infinity over negative infinity form. So let's try another one here. So I I actually don't know where I I think I lost a page here and I don't know where the page went to. Oh, okay, so let's try the next one. This one is for the form of infinity minus infinity. All right, so infinity minus infinity. So here we go. So limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1. So notice that this is actually 1 over 1 over infinity minus 1 over no, that's not right. Nope, nope. That's not actually. That's actually not right. I actually feel like I've lost I lost it because I was looking at something weird on the flickering screen again, which I don't know again why this is doing this to me. It seems like it would not do that to me, but anyway. All right. So just try to remember that as the x is approaching one from the right, that this will be infinity minus infinity. All right. So I don't want that. So what am I what am I going to need to do? All right. Why don't I find the common denominator here? So if I find the common denominator, it will be limit as x approaches 1 from the right of, all right, so x minus 1 minus natural log of x all over x minus 1 times the natural log of x. All right, so all I really did here was find the common denominator here. So now I I verify whether or not I can use the L'Hopital's rule here. Well, all right, 1 minus natural log of 1 over 1 minus 1 times natural log of 1. Well, that's 0 over 0 now, so I can use L'Hopital's rule. So now I will go ahead and I will just find the derivative of the numerator over the derivative of the denominator. So it's limit as x approaches 1 from the right, derivative of x is 1, derivative of natural log of x is 1 over x. Then we need the product rule here in the denominator. So use the product rule. So the u is x minus 1 and the v is natural log of x. So u prime is 1 and v prime is 1 over x. So we have the natural log of x, then plus x minus 1 times 1 over x. And now I verify whether I can use the L'Hopital's rule or not. So here is one issue that I really have here. I see that 1 over 0 is undefined, so I need to take care of that no matter what, right? So, wait, actually, 1 over 0. Did I say 1 over 0? No, yeah, well, yeah, it was 1 over 0, but just just here get let's just get it together here. All right, so 1 minus 1 over natural log of 1 minus 1 times 1 over 1. So that will be 1 minus 1 over 0 minus a 1, which will be 0 over negative 1, which is 0. So actually, believe it or or not, this actually is not what something does not seem right here. And I don't actually know where the um I actually don't know where the issue is, where the issue I don't actually know where the issue is. Oh, because I wrote a plus there and a minus here, so plus. All right, so that will be 0 over 1, which is actually 1. Uh, why do I not see it here? This is something is not actually something actually seemed very strange to me here, because this should be 0 and then 1 minus 1 is 0. Yeah, so 0 over 0 is not 0. It was two things. It was definitely me. I promise that it was me who made a subtraction error there. So that means I can use the L'Hopital's rule again, right? Because I still have 0 over 0. So now we have the limit as x approaches 1 from the right. Now, what I'm actually going to do here to maybe make the L'Hopital's rule a little bit easier is distribute the 1 over x. So I have natural log of x plus x over x minus 1 over x, or just natural log of x plus 1 minus 1 over x. All right, so then the derivative of 1 is 0, and the derivative of 1 over x is, so that's negative x to the negative 1. So it is, well, what does it give you? That is going to be x to the negative 2, or 1 over x squared. All right, 1 over x squared. And then this is going to be the derivative natural log of x is 1 over x. The derivative of 1 is 0. And then the derivative of the negative 1 over x we just saw was 1 over x squared. So now, what do I see here? Well, I can just substitute the 1 now. So I have 1 over 1 squared over 1 over 1 plus 1 over 1 squared. So it's 1 over 1 plus 1. So it's 1 over 2. All right, 1 over 2. So that limit is equal to 1 over 2. All right, let's try another one here. So what do we have for the next one here? So the limit as x approaches 0 from the right of cosecant of x minus cosecant of 2x. So as you can suspect, this is one where you probably have an indeterminate form that you don't like, but if you use sines and cosines, you could probably get rid of this fairly easily, right? So limit as x approaches 0 from the right of, well, this will be cosecant of x is 1 over the sine of x, then cosecant of 2x is 1 over the cosine, sine of 2x. And then now, what do you notice here? Well, all right, if you're approaching 0 from the right, then this is actually infinity minus infinity form. So we need to rewrite this. So again, one common way to do that is to find the common denominator. So this will be limit as x approaches 0 from the right of sine of 2x minus sine of x, and then all over sine of x times sine of 2x. And then let's see what we have here. So we have in the numerator, we have 0 minus 0, and then the denominator 0 times 0. So we have 0 over 0 form, so we can use L'Hopital's rule. So let's use L'Hopital's rule. So we have limit as x approaches 0 from the right. The derivative of sine of 2x will be the negative, well, I don't want to put negative, so just cosine of 2x times 2, then minus the cosine of x all over. now we need the product rule here. So use the product rule here. So the u will be sine of x and the v will be sine of 2x. So u prime is cosine of x and v prime is 2 cosine of 2x. So again, if you have any questions, please feel free to ask. But again, I'm just double checking to make sure every step that I can actually use L'Hopital's rule. All right. So then I have the cosine of x times sine of 2x. Then we have plus sine of x times 2 cosine of 2x. So what do we have here? Well, we have, all right, so, well, if you look at what you have here, you have, oh boy, well, cosine of 2 times 0 is 1, so 1 times 2 minus the 1 over 1 times 0 plus, then we have sine of x 0 and then times 2 times 1, so we have, well, that will be negative 1 over 0. So what are you going to do here? Well, all right, so you know that you can't actually substitute the 0 in directly, but if you substitute a number that is really close to 0 in here, then what do you know will happen here? Well, all right, so sine of let me get out my calculator to make sure that I prove this point to you. Um um that what you really want to do here is just try to here. I'll show you. All right. So remember, this was originally like 1 over sine of x and then minus 1 over sine of the, where is it? Sine of 2x. And then if you graph this and you want the limit as x approaches 0 from the right, I hope that you can see that what you get here is using the table here, you get something where it is, well, error, that doesn't help you, does it? Okay. 0.000001, you get some really large number. So actually, if you actually substitute a number to the right of 0 in here, then you would see that this does actually go to infinity. All right. So sometimes, like trying to figure out what this is, oh, that should be 1. I just realized I wrote a negative and not equal sign, but sometimes trying to figure out what this is, eh, I just use a numerical calculation to figure this out and finish it off for good. All right, so now let's try another one here. So here are some other indeterminate forms. So 0 to the 0, infinity to the 0, or 1 to the infinity. So to evaluate these types of limits, here are the steps that you are given here. So here is the first one here. So you need to calculate the limit as x approaches the value of g of x times the natural log of f of x equals L, and then find e to the L. So what we're going to do then is exactly what this says here, because if you look at this, this is actually of the form 1 plus 0 to the infinity, or 1 to the infinity, so we can't actually do this limit. So we're going to calculate the instead of this limit, we're going to bring the x down in front and then take the natural log. So limit as x approaches infinity of x times the natural log of 1 plus x. All right, and now what do you have here? Well, that's infinity times natural log of 1 plus 0. So that's actually infinity times 0. So we can't find that limit either. So we need to go ahead and find a common denominator inside of the natural log argument here. So it's x times natural log of x plus 1 over x. And now we are going to use the rules for logarithms. So I found the find common denominator, and then I'm going to use the rules for logarithms. So the log rules here. So this will be a limit as x approaches infinity of x times, and this will be natural log of x plus 1 minus natural log of x. And then I hopefully see here that I can go ahead and, well, this is going to be a tricky one. All right, so I do want you to realize that this is not actually as as easy as it looks, because you still actually cannot do this one. So see how this is to the first power, right? So I'm actually going to rewrite this in the denominator as it being to the negative 1 power. So if I bring it back to the denominator, it's to the negative 1 power. And so why would I want to do that? Well, then this is the limit as x approaches infinity of x all over 1 over natural log of x plus 1 minus natural log of x. And then I can see that I can combine these back together. So I may have been taking you in circles, but in a way, I I honestly did not intend to take you in circles. So I'm actually not, well, believe it or not, I'm not going to take you in circles. Actually, I'm just going to let's see. Yeah, what I'm actually going to do is just say that this is infinity over infinity form now. So you can substitute in some values for x and see that the denominator would go to infinity. So now I can use the L'Hopital's rule here. So this will be limit as x approaches infinity. The derivative of this is going to actually be the what do you want to call it? The 1, and then I will go ahead and you can use the quotient rule here if you want. All right, it's up to you if you want to use the quotient rule or how you want to do that, or the power rule, because if I want to find the derivative of this, it's just negative 1 and then natural log of x plus 1 minus natural log of x to the negative 2 power, and then the derivative of the inside part for the chain rule. So that will be 1 over x plus 1 minus 1 over x. So what you have here, if I bring this back to the denominator, all right, so I have negative, and I'm telling you, this is crazy here. So 1 over x plus 1 minus 1 over x, and then all over the natural log of x plus 1, then minus natural log of x to the second power, all right? And really, this is what you would have gotten using the quotient rule anyway, because it would have been 0 minus this, because the derivative of 0, well, derivative of 1 would be 0, all right? And so then it would have been 0 minus this all over the denominator squared anyway. So then, all right, so what is this going to be now? Well, if I go ahead and I I multiply by the reciprocal here, I have the limit as x approaches infinity, and so this denominator is on the numerator now, so I have natural log of x plus 1 minus natural log of x all squared all over the negative 1 over x plus 1 minus 1 over x. And then what do you have now? So I can go ahead and figure out what is happening here. And this ends up being a case where I actually have a well, all right. So you 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 have to use you have to use L'Hopital's rule again here, and so oh oh boy. All right, so yeah, if you use L'Hopital's rule again, or if you don't want to use L'Hopital's rule again, then what else could you do? You could actually find a common denominator at this point, and I actually don't know if let's try to do that. Let's just to see if that would help to find a common denominator of this again. All right, just because I feel like that actually would help to figure out what this would end up being here. All right, so if you have a limit as x approaches infinity of natural log of x plus 1 minus natural log of x squared all over negative. So that will be x minus x plus 1 all over x times x plus 1. And so then what do I have here? I have the limit as x approaches infinity of natural log of x plus 1 minus natural log of x all squared, and then times multiplied by the reciprocal, so negative uh, x times x plus 1, and then that will be over the negative, and that will be negative x, and then that will be a plus, so then negative x. All right, and then a. Whew, okay, so then, well, actually, I don't want the negative here then. All right, there, I won't put the negative there. All right, that might actually make it easier for you. It's up to you. All right, well, maybe actually I'll just put it there, and I won't distribute that. That will be fine. We won't distribute that. I won't even put you through all that hassle then. I thought that I might put you through all that hassle, but I don't. I really don't want to. So x minus x plus 1, then distribute this. So we have just a 1 in the denominator. So this is limit as x approaches infinity of negative x times x plus 1, and then times the natural log of x plus 1 minus natural log of x squared. So at this point, let me just reiterate one thing that for this particular problem here, and let me I'm I'm gonna look up the theorem that I want to tell you because I feel like there is a theorem that would make this a lot easier for you, but I don't remember the exact wording of it, and I don't want to mislead you here because I feel like this problem already probably put you through something that you may not have wanted to go through, right? So if one of these things sort of happens to you, then all I would say here is that where is it? Where's the original problem here? Because this was happening to me yesterday where my screen went blank and I couldn't find it. So let me go ahead here. Okay, so here was here's this, and if it seems like you're going in circles, then all right for this one. All right, so the limit as x goes to infinity of 1 plus 1 over x to the x. This actually should seem like one that you have seen uh, before here, and where is it? What is the name of it? Is the guy's name like I can't. If I could remember the guy's name, then I would have a lot better um idea of like what is like where I looked this up in the index of the book because this is actually just bothering me that this is um happening like this here. So all right, so now remember that this is what actually no, don't tell me. This is this is I, I'm laughing here, but I bet that this is like one of those cases where I want to remind you about something that you probably have heard about before. Do you remember the limit as x approaches infinity of, and this one is one that we've found before, by the way. All right, so it was 1 plus, all right, uh, r over x to the x. And I told you a long time ago that was e to the r, right? So then in this particular case, then this r was actually equal to a 1. So then this would actually be e to the first power, which is just e. All right, so just try to remember that that's what this is, um, that this is what this is actually going to be here. All right, so um so in my opinion, the thing that I would recommend doing is huh well, I'm not even sure that I would recommend doing that, but I, I would, okay. So here's what I'm gonna recommend. If you see that you're going in circles like this, all right. Here is a another approach. All right, I would just recommend abandoning it and either doing this numerically or taking another approach. So here would be another approach. So here is the x and then times the natural log of 1 plus 1 over x. All right, now remember how I originally took this and brought it into the denominator, right? Let's say I reverse course and instead of bringing this into the denominator, I brought the x into the denominator. All right, so that would be x to the negative 1. All right, and then that would be limit as x approaches infinity of natural log of 1 plus x over 1 over x. And so then I actually have a case where I have a 0 over 0, and I can use L'Hopital's rule. And so then this will be limit as x approaches infinity of, all right, so using L'Hopital's rule, of the derivative of the numerator is 1 over the 1 plus 1 over x times the derivative of 1 plus 1 over x, which is negative 1 over x squared, and then the derivative of the denominator is negative 1 over x squared. So then these sort of divide out, especially since x is not equal to 0, it's actually approaching infinity. So then you have 1 over 1 plus, and as x goes to infinity, that's 0, so 1 over 1, which is 1, and then if you remember the rule, this said to do e to the L. So then e to the L in this case would be, so this is L. So L is equal to 1. So therefore e to the L is e to the 1, which is e. So in my opinion, the only two things that you can do are, one, you can bring this to the denominator like I did and make that to the negative 1 power, or you could bring the x to the denominator and make that to the negative 1 power. But my whole point was, and there's a name for it, and I still can't remember the name of it, so that's making me upset here. My whole point is that if you see that you're cycling through and you're not going anywhere, then this might mean that you actually dealt with the exponent incorrectly there, and you need to take the other factor into the denominator to the negative 1 power. All right, or you could just compare it to this limit that we've had before and say, well, I knew that limit from before, and so that should be e to the r power, and that means that this is e to the first power, and that means that it's equal to e. So unfortunately, like that's how it goes, is that your first attempt may not look like it's a very easy thing to do, but that's all I was trying to get across, is that some of these look like they are easier than they really are, but then you see that you're looping around and you need to try a different method. All right, so unfortunately that is the end of this section.